Hello, everybody. So, kind of continuing on, we're going to do one more section on 5.2, one more video, 5.2 part 3. And I did get cut off a little bit earlier when I was doing 43 on the last video, so I didn't get all the way through that one. So I will start with that one again. I am going to pick the left-hand side. On this one, I actually could pick either, but for right now, I'm going to pick the left-hand side because it looks more complicated. It's not really that much more complicated, but we'll pick it and see what happens. Okay, so I've got this cosine alpha over secant alpha plus sine alpha over cosecant alpha. And if I were to rewrite that, so if I were to bump the secant up, that would become a cosine. So I'd have a cosine alpha times cosine alpha. And if I were to bump the cosecant alpha up, that would become a sine. So I would have plus sine alpha times sine alpha. And this all together is going to be cosine squared alpha plus sine squared alpha. But what's cosine squared alpha plus sine squared alpha? It's 1, right? So this is a 1. Now, somehow this 1 is equal to the right-hand side. And we just need to think about why that is. So remember, we have this identity that says that 1 plus tangent squared alpha is secant squared alpha. If I am to subtract tangent squared alpha from this, both sides of this equation, I would get 1 equals secant squared alpha minus tangent squared alpha. That is another form of this identity. So once we get to 1, I literally know that 1 is secant squared minus tangent squared. So I can go ahead and replace that. Secant squared alpha minus tangent squared. Because that's one of our identities, right? Something that we would know from one of our Pythagorean identities. And then I have QED. Like I said, one of my favorite proofs right there. I think that's a neat one. Okay, number 45. So this one I've got sine to the 4th theta minus cosine to the 4th. I want to show that that is 2 sine squared minus 1. Okay. So I kind of picked that left-hand side. I noticed that that is a difference of squares. So I'll pick that left-hand side. That's sine to the 4th theta minus cosine to the 4th. And the question is, well, how do I factor that? Well, remember, I know that something like x to the 4th minus y to the 4th, that would factor as x squared plus y squared, x squared minus y squared, right? Because it's just a difference of perfect squares. Okay, so how is this guy going to factor? Well, this guy is going to factor as sine squared plus cosine squared and sine squared minus cosine squared. And you can check pretty easily that that is going to work out. Sine squared times sine squared, sine to the 4th. These middle two sine squared, cosine squareds are going to cancel. And then cosine squared times negative cosine squared, that's minus cosine to the 4th. So we factored it. Now, great thing about this is that this part right here is going to be a Pythagorean identity. So that is 1, that cosine squared plus sine squared. So I really just have 1 times this. Another way is I just really just have sine squared minus cosine squared. I just have 1 times that, and I just have that. And if you want to write in 1 times and then write this, that's fine too, but either way, I have that. Now, that's still not quite what we have. So I have 2 sine squared minus 1. Here I have sine squared minus cosine squared. So I still have some work to do. Now, in this one, everything is in terms of sine squared. So that's like a big clue in. I need to get this expression entirely in terms of sine squared. So to do that, there has to be a way that I can rewrite cosine squared in terms of sine squared. Well, remember our identity, right? Cosine squared is 1 minus sine squared. That's from our Pythagorean identity, right? So what I would do here is, since I know that cosine squared is 1 minus sine squared, I would replace cosine squared with 1 minus sine squared. You just have to be careful to put parentheses around that 1 minus sine squared because I'm distributing that negative there. So I would have something like this. This would be sine squared minus 1 plus sine squared. Altogether, that's 2 sine squared minus 1. Okay, and QED. I've got my right-hand side. Okay, let's take a look at 47. So hopefully this one's not too bad. And again, another kind of cool identity. Pause it if you need to. (47) 1 minus cosine over 1 plus cosine. Okay, and if we do that, apparently that's cotangent minus cosecant squared. Okay, so this one is going to be kind of interesting about which way I would pick. In fact, I might want to argue that I would want to think about it maybe two different ways to do this, to show you kind of the connection here, an important connection. So I think what I'll do first is I'm going to mix it up for the first time in trig history, just for these video series. I'm going to pick the right-hand side and the cotangent minus cosecant squared and try to simplify that to get the left. So we'll see what happens. Okay, so this right-hand side, I would have cotangent x minus cosecant x squared. And then I would simplify this. So this is cotangent x minus cosecant x times cotangent x minus cosecant x. Okay. And at that point, you could either write everything in terms of sine or cosine, or we could go ahead and just kind of distribute it first. For our purposes here, I think we'll just go ahead and distribute. So this is cotangent squared minus cotangent cosecant minus cotangent cosecant, and then minus cosecant times minus cosecant is positive cosecant squared. So this is going to give cotangent squared minus, actually, well, I'll go ahead and write like that first. Cotangent squared minus 2 cotangent cosecant, just collect those like terms, plus cosecant squared. And right now, we might be a little scared, and we're like, well, how on earth would we actually get that left-hand side? Because you might be thinking, well, it looks nothing like that left-hand side. Well, I haven't written it in terms of sine and cosine and see what happens yet. Okay, now I know cotangent is cosine over sine, but cotangent squared is cosine squared over sine squared. Cotangent squared is cosine squared over sine squared. This guy is minus 2 cosine over sine times 1 over sine, right? And this guy is 1 over sine squared. This is going to be really pretty. And I'm not an artist, but this feels like art. Okay. This is cosine squared. Now, you may notice that this is sine squared. So I actually have a common denominator here. This guy is just sine squared, sine times sine. So I can combine all the numerators. So I really just have cosine squared minus 2 cosine x plus 1 over sine squared. Okay. And then to kind of factor the numerator out, how do I factor this? Well, what multiplies the 1 and adds the negative 2? That's negative 1 and a negative 1, right? So this is cosine x minus 1 times cosine x minus 1 would be how this factors in the numerator. Now, if I just leave this as sine squared in the denominator, I might be stuck here all day. I might say, well, we failed. Well, no, we didn't. Everything's in terms of cosine here. I can get sine squared in terms of cosines. So what's sine squared? That is just 1 minus cosine squared, right? And then I would keep going. So I would have cosine x minus 1, cosine x minus 1. And then this guy here, 1 minus cosine squared, that's a difference of perfect squares. So that's 1 minus cosine, 1 minus cosine. And then what we would need to do, well, we would need to factor out a negative. Oh, sorry. I was just saying what is going. One of those is a positive, right? That's a difference of squares. 1 minus cosine squared is 1 minus cosine times 1 plus cosine. Okay, so this factors as this. Okay, and then I would still need to cancel out one of these factors. So what would have to happen is I would have to pull out a negative from one of these. So maybe I pull this first factor out, and if I pull a negative 1 out of this cosine minus 1, it would become 1 minus cosine like that. I would get this. And then pause it if you need to. I'm going to kind of work back this way. What would then cancel out? This 1 minus cosine, right? So this would really give me negative 1 times cosine minus 1 over 1 plus cosine. Now, that's almost what I have here. You might see the only difference is they distribute the negative, right? The negative 1 times cosine is negative cosine. Negative 1 times negative 1 is 1. So really this is just 1 minus cosine if I distribute over 1 plus cosine. Finally, the QED. Okay. Now, do you want to see the other way? Well, the other way, what would you have to do? Well, if I was starting from the other way, I would have to do something a little quirky. So let me just show you how we would start that. Erase this part. Okay, so if I pick this left-hand side, I wish I hadn't erased that on the right-hand side over here. But if you notice here, what I just erased, I had like a 1 minus cosine and a 1 plus cosine. Right? That is what we kind of got to in the end. 1 minus cosine is the conjugate of 1 plus cosine. So kind of a common like strategy, which is something you can try if everything else is kind of going to fail basically, is multiplying by the conjugate. That comes up a lot if we're using these Pythagorean identities. So if I have one like this, and I can't do anything else with it, one strategy you can try to use is to multiply by the conjugate of the denominator. Sometimes also the numerator, but it depends on the question. But on this one, it would be the denominator, and I would multiply. My first step would actually be to multiply by 1 minus cosine, because that's the conjugate of the denominator. So if I started with the left-hand side, my first step would be something like this. And then I would go on and be simplifying that. And to save some time, I'm not going to do that because it's kind of what we did the other way in reverse. But we are going to see some like that where it's a little more clear-cut that I would want to implement that multiplying by the conjugate strategy. And for instance here, I've got kind of the same amount of work, so it doesn't really matter which side. But if I pick that left-hand side, it is going to be a multiplying by conjugate problem. And then I'm going to have to distribute that out and simplify a lot of stuff. So that would be kind of what our strategy. That right-hand side that we just did, showing it's the left-hand side, that is perfectly fine on that one. Okay? And we got to use the right-hand side for once. Okay. Let's look at some more. So 51 I've got down here. One over 1 minus sine plus 1 over 1 plus sine show that this is 2 times secant squared. Okay, so left or right? Well, it would be left. And I would write this out, 1 over 1 plus sine plus 1 over 1 plus sine. How would we get a common denominator there? Well, I would have to multiply this guy by 1 plus sine and this guy by 1 minus sine, right? So we would have 1 minus sine. Sorry, I meant 1 plus sine times this guy. And then the other one I'm doing 1 minus sine, right? Okay. And then going through and simplifying all that. So here I've really got 1 plus sine. And then over here I've got plus 1 minus sine. And all that is over 1 plus sine times 1 minus sine. You may notice that numerator is just 2. So 1 and a 1 is a 2. The sine minus the sine cancels. And then down here we've got 1 minus sine plus sine. Those cancel. Sine times minus sine is minus sine squared. So I got 1 minus sine squared. So this is really 2 over 1 minus sine squared is cosine squared. And 2 over cosine squared, if I move this guy up, right, that would become a secant squared. So this is 2 times secant squared. So notice the strategy really wasn't to multiply by the conjugate because we had to. It ended up being like that because I was combining those fractions, and it ended up we were kind of multiplying by the conjugate on both of these. But you see when I did that I ended up with this Pythagorean identity down here that gave us cosine squared. So that's another problem where even if we're not directly multiplying by the conjugate, it kind of comes up and you can see how it is useful. Okay, so that one's good. 57, I say. Okay, this one looks bad, but it's actually not too bad. So 57. And the only time, if they're using S, I really hate writing that letter out. Feel free to use, say, X, let's say, okay? Change the S to an X. I can't write the S So like 57, I'm going to say this is secant to the fourth x minus tangent to the fourth x. It's just a pain if you have to write it over and over again. Secant squared plus tangent squared. Okay. So originally, actually, I don't do anything with the denominator yet. Oh, I need to write a right-hand side. Sorry. Didn't write my right-hand side out. I'm going to pick the left-hand side because it's more complicated. So I've got secant to the fourth minus tangent to the fourth, and then over secant squared plus tangent squared. Numerator is going to factor as secant squared minus tangent squared times secant squared plus tangent squared. So that's a difference of perfect squares over the denominator, which is secant squared plus tangent squared. Now, so if all I did was honestly just factor the numerator, these cancel, and we have it. We got it. I didn't actually use any of my Pythagorean identities, so, and I got what I wanted to prove, and that's QED. That's it. So they can be that simple. Okay, 63. This is a little tricky one. Let's do it. So I got sine squared alpha, secant squared alpha, plus sine squared alpha, cosecant squared alpha equals secant squared. Okay. Now, there's a couple ways you can do this one. All right. Several ways. I think you want to pick the left-hand side. And then I've got kind of a cool way, kind of a 360 dunk kind of way to do it. And I guess I'll show you that way. And then just kind of point out that you would get it even if you did it another way. But left-hand side, sine squared times secant squared plus sine squared cosecant squared. I look at this, I see all the squareds, I see the secant squared. I'm like, boy, it would be nice if this is somehow 1 plus tangent squared in disguise on the left-hand side. That's what I'm thinking. And then if I look at this a little more carefully, that's exactly what we've got. Let me explain. I move this secant squared down to the denominator, it becomes a cosine squared, right? So really this is just sine squared. If I move the secant squared down, it's cosine squared. If I move this cosecant squared, it would become a sine squared if I move it down. Or just write it as 1 over sine squared. Either way, this is actually just 1, right? So sine squared times cosecant squared is 1. This is just tangent squared, sine squared over cosine squared. And then what's tangent squared plus 1? That's just secant squared. So that would be the easiest way to do that one. Now, could I make it a little more difficult? Yeah. But I could get there if I did. Okay, so that's perfectly fine way to do it. No problem with that at all. Let me show you what would happen so that if you do this, you would still get it eventually if maybe I start by factoring out a sine squared. Maybe I see, okay, there's a sine squared in there. It looks like it's a good idea to factor it, even though it really might not be here. And then I rewrite these. Secant squared is 1 over cosine squared, and this guy's 1 over sine squared. And if I add those together, I would need a common denominator. So really, at this point, I could either distribute and see what I had before, which is get it, or I could combine these. Maybe, so it's kind of like making another error, but let me pretend that I do that. So it's like sine squared over, sine squared cosine squared. So multiplying this guy by sine squared, multiply this guy by cosine squared. So let's pretend we still don't see it. And then I have sine squared, and then sine squared plus cosine squared over sine squared cosine squared. I would still get there, because that is just a 1 right here, right? So I've got sine squared 1 over sine squared cosine squared. And then you may notice that this sine squared cancels. So I get 1 over cosine squared, which is the secant squared. I'll move it up. Is this way harder? Yes, absolutely. Did I know that beforehand? Well, probably not if you haven't done it before, right? So my point is, even if sometimes we take the longer route, as long as I'm doing the identities, typically eventually we'll get there. Are there some trickier ones? Yeah. But typically, we're using our identities, we're going through, as long as we're doing the algebra correctly, we'll get there. Was this the quickest way to do it? No. So it's not the best way to do it. The best way would be to rewrite this initially, which we've seen sometimes works well, sometimes doesn't. So it kind of depends on the problem. Okay. Right, at the 27-minute mark. Which other one did I want to do here? So I had 5, 2, and I just did 63, right? Okay. All right, I think I will make a part 4. I know I'm recanting on what I said, but the video is stretching on. I'll make a part 4 and stop this video here.